Hello, and welcome to Space for Sleep. I'm genuinely so glad you found your way here tonight. Maybe you're resting in the soft glow of your room, the noise of the world fading into background silence. Wherever you are, let your thoughts drift for a while. This is a space where wonder and rest can coexist, where the mysteries of the cosmos can be explored without hurry. Tonight, we'll follow a strange traveler, a visitor from beyond our sun's domain, a fragment of another world, perhaps even another star, whose path through our solar system has raised questions scientists are still trying to answer. Its name is 3I Atlas, and when it reached its perihelion, its closest moment to the sun, something unexpected happened, something that didn't quite fit any of our models, something strange. Interstellar objects are rare visitors. In all of recorded history, we've only confirmed a few. The first was a Oumuamua, discovered in 2017, a long, tumbling shard that swept past the sun and left astronomers arguing about whether it was a rock, a fragment, or something entirely new. Then came 2I Borisov, an icy comet-like body that behaved more like something we'd expect, until we realized it was traveling too fast, its origin clearly beyond the Oort cloud. And then, years later, came a faint signal, a small blur of light catalogued by the Atlas Survey, the asteroid terrestrial impact last alert system, from an object that didn't belong here. It was moving too fast, its trajectory unmistakably interstellar. They called it 3I Atlas, marking it as the third interstellar object ever detected by humankind. At first, it seemed like just another icy visitor, a comet from another star system, maybe even a remnant of a distant planetary disk. But as it neared the sun, instruments started noticing subtle discrepancies. Its brightness didn't behave normally. The reflection pattern of sunlight off its surface didn't match its size. And as it approached perihelion, the point in its orbit where it should have shed dust and gas in predictable streams, it didn't. Not the way any comet would. Something about it resisted explanation, and for scientists watching from observatories across the world, it became an enigma worth losing sleep over. Picture the solar system for a moment, the planets orbiting in quiet ellipses, the sun burning with relentless fusion at the center. And then, cutting across all of that like a cosmic arrow, a visitor enters. It doesn't belong to the gravitational family of our sun. It's not captured, it's not born here. It's just passing through, following a path set in motion millions, maybe billions of years ago, a messenger from somewhere else. That's what makes 3I Atlas so fascinating. It's a physical fragment of another system's story. Every atom on its surface could tell us about a sun that isn't ours, about worlds we'll never see. But the universe rarely gives up its secrets easily. The first thing astronomers noticed was how quiet the comet seemed. Most comets, as they approach the sun, begin to boil off material. The heat ignites a spectacle, glowing gas tails, jets of vapor, bright halos of dust. They become vibrant, visible even through small telescopes. But 3I Atlas, as it neared its perihelion, didn't behave that way. Its coma, the cloud of material surrounding it, was dim and oddly uniform. Its tail lacked structure, and yet, paradoxically, its brightness fluctuated in ways that suggested internal activity. It was almost as if something inside was trying to release energy, but the surface wouldn't let it out. This led some to suspect that 3I Atlas might not be a traditional comet at all. It might be fragmented, perhaps partially hollow, or covered in a crust that sealed away volatile ices beneath its surface. In short, it might be a fossil of interstellar travel, a body scarred and reshaped by eons drifting between stars. The sun's heat, instead of awakening it, might have revealed the damage it already carried. Ancient fractures, strange reflections, inconsistent outgassing. But the real puzzle came at perihelion itself, that moment when it swung closest to the sun. Instruments tracking its spectral lines, the specific fingerprints of light emitted by its materials, picked up something no one expected. There were molecular traces that didn't match any known cometary composition from our solar system. Some of the ratios between carbon and oxygen isotopes were distinctly off. They suggested a formation environment unlike anything in our local neighborhood. In simple terms, this thing wasn't just from far away, it was from a place where the chemistry of creation itself might have been different. The story of 3I Atlas is, in a sense, the story of how our universe reuses its materials. Every star, every planet, every human atom is recycled stardust. When a star dies, it scatters its elements into space: carbon, oxygen, nitrogen, metals, the ingredients for the next generation of worlds. Over millions of years, these clouds condense again, birthing new suns and planets. But the differences in those environments, temperature, radiation, elemental abundance, can shape the kind of bodies that emerge. If 3I Atlas carries a chemical fingerprint foreign to our solar system, it's like holding a sample from another universe's kitchen, a taste of alien cosmic history. As it passed its perihelion, something else changed. Its path through space began to deviate slightly, not dramatically, but enough that the data analysts noticed. It wasn't behaving like a purely gravitational object. There seemed to be a small non-gravitational acceleration, a subtle push, as if sunlight itself was nudging it harder than expected. This echoed what we saw with Oumuamua. That object, too, had accelerated slightly after passing the sun, leading to endless debate. Was it outgassing, radiation pressure, or something we didn't yet understand? For 3I Atlas, the effect was smaller, but still unmistakable. And that opened up the same old questions. What exactly was propelling it? Could it be that the surface was reflecting sunlight more efficiently than we thought? Maybe it was thin or coated with an unusually reflective layer. Or perhaps, just perhaps, we were seeing the first signs of a natural object that behaved almost like a light sail, propelled gently by radiation, a relic of cosmic engineering or an exotic fragment from some long-dead star system. Of course, in science, the simplest explanations must always be tested first, and many astronomers lean toward natural causes: material composition, sublimation irregularities, observational errors. But even those explanations leave room for wonder. Because no matter how we describe it, 3I Atlas is not from here. Its trajectory, its chemistry, its light curve, all point to a world we can only imagine. When the data first came in from the Atlas survey, the object was faint, nearly lost against the background of space. Observatories across Hawaii and the Canary Islands coordinated to track it, logging its light over days and weeks. As it neared the sun, the activity spiked, then dipped again, unpredictably, and then came the perihelion, that tight, glowing arc where sunlight should have overwhelmed it. But it didn't. The object's signal remained steady, almost stubbornly calm. Some astronomers described it as a dead comet, a body whose internal ices had long since evaporated during previous passes through other system stars. Others called it a ghost of a comet, something that once lived but now drifts as an inert shell. Yet that theory conflicted with another set of data: thermal readings suggesting internal temperature fluctuations inconsistent with a completely dead core. Something was happening inside, even if the surface refused to show it. Imagine that. A comet carrying buried energy, its secrets sealed beneath layers of cosmic scar tissue. The sun's warmth tries to wake it, but the memories of a colder, harsher galaxy keep it asleep. It's a haunting image, but one that fits the evidence. And if true, it might tell us more about how matter evolves as it journeys between stars, about how time, radiation, and cosmic dust sculpt the relics that wander into our sky. When scientists modeled 3I Atlas's path backward, they found that it came from a direction roughly aligned with the constellation Cassiopeia. That doesn't mean it came from a particular star there. Interstellar space is vast, and small objects drift chaotically under gravitational tugs over millions of years. But it gives a poetic symmetry to imagine it starting its journey near a shape we can recognize in the northern sky, the W of Cassiopeia, before crossing the interstellar gulf to find its brief moment in our sun's light. By the time it left the solar system again, 3I Atlas had grown fainter, almost undetectable. The sun had shown us only a fraction of its mystery, then let it go. What it left behind were data points, graphs, spectral lines, and a question that no one can yet answer: what exactly happened during that perihelion? Was it a simple play of light and ice? Or did the sun briefly illuminate something deeper, something about how the universe builds and recycles its wanderers? Perhaps, as we drift through the quiet of the night, the answer isn't just in the data, it's in the reminder that every strange visitor, every unexpected anomaly, is a message from beyond, an invitation to look closer, to imagine wider, and to keep wondering. As 3I Atlas drifted away from the sun, the attention of astronomers turned towards something more subtle, the question of how and why it moved the way it did. In the vacuum of interstellar space, every motion tells a story. Each tiny deviation, each flicker of light, is a signature of hidden forces. With 3I Atlas, those signatures whispered of physics we didn't fully expect to find in a comet. Its non-gravitational acceleration, that faint, almost ghostly push, wasn't random. It was systematic, measurable, and persistent. To understand why that mattered, you have to think about what usually propels a comet. When sunlight heats its icy surface, the frozen gases trapped inside begin to vaporize. These escaping jets of gas act like thrusters, pushing the comet slightly in the opposite direction. It's a process called outgassing, and it's completely natural. But the key is predictability. Outgassing follows certain thermal patterns. It responds to sunlight intensity and rotation. In 3I Atlas's case, the acceleration didn't match any of those expected signatures. It was too clean, too consistent, and not nearly strong enough to match the energy that a typical outgassing event would require. That discrepancy led some to suspect a different mechanism at play, perhaps radiation pressure. Light itself carries momentum, and when photons hit a reflective surface, they can push against it. Normally, for a comet or asteroid, that effect is minuscule, far too weak to cause measurable acceleration. But with Oumuamua, and now 3I Atlas, the push seemed just a bit too large to ignore. The logical explanation would be that these objects were unusually light for their size, perhaps thin or hollow, or made of a porous material that gave them an abnormally high surface area to mass ratio. If that sounds familiar, it's because it parallels an idea that sparked controversy years earlier, the notion that Oumuamua might have been an artificial light sail, a relic of alien engineering. For 3I Atlas, most scientists hesitate to go that far, preferring natural explanations. But the echo of that possibility lingers in the background of every discussion. Because if both of these interstellar objects, the only two with measurable non-gravitational acceleration, share this trait, then perhaps there's something universal about the way matter forms and evolves in interstellar space. One line of reasoning suggests that interstellar travel is harsh enough to strip away almost everything but the most resilient structures. Cosmic rays, dust impacts, micrometeorite collisions, all of them sandblast an object over millions of years, carving it down, hollowing it out, turning it into a kind of cosmic shell. What remains could be a wafer-thin crust, not unlike pumice or aerogel, a material so porous that sunlight could push it slightly off course. It wouldn't take alien design to make it so, just time, just physics. But time and physics alone don't fully explain what happened at Perihelion, because there was another puzzle, a thermal one. As 3I Atlas approached the sun, models predicted its surface temperature should rise in a smooth curve, driven by solar radiation. Instead, observations showed irregular heat patterns, as if some regions of the surface were reflecting heat rather than absorbing it. A cometary body with a highly reflective surface, something coated in silicate dust or metallic compounds, could behave this way. But for an object formed in deep interstellar cold, that composition would be highly unusual. So, where could such materials come from? Perhaps from a catastrophic event, the explosion of a nearby star, or the violent formation of a binary system, where debris was ejected at extreme speeds. It's possible that 3I Atlas was once part of a planetesimal, a building block of a planet that was torn apart before it could ever settle into orbit around its home star. Its surface, rich in metallic oxides or crystalline silicates, could have been fused by ancient heat, turning it into a reflective shard of cosmic glass. If true, then its perihelion brightness wasn't the sun igniting its ices. It was sunlight glinting off an alien crust. Spectroscopic studies supported part of that idea. The carbon-to-oxygen ratios recorded didn't match typical solar system comets, and the faint trace of magnesium-rich silicates pointed toward high-temperature formation. In other words, this object might have originated close to a different star, not far out in the cold outer regions where most comets form. That alone made it an oddity, a comet born in heat, not ice. A traveler from a system where worlds might have formed closer to their suns, and where materials fused and melted before being scattered into space. When you consider the timescales involved, it's dizzying. For an object like 3I Atlas to cross the gulf between stars could take millions, even hundreds of millions of years. Along the way, it would pass through vast, empty stretches of interstellar medium, regions filled with dust, radiation, and magnetic fields. Every collision, every burst of radiation would change it. It's no longer just a rock or a comet, it's a record of the universe's memory, written in molecular scars. The perihelion then becomes a kind of cosmic interrogation. When our sun's heat touched it, it revealed the long story of how matter ages in the dark. One of the strangest findings came from polarization data, the way light scatters when it reflects off a surface. Astronomers analyzing the polarization curve found it to be anomalously smooth, meaning that the surface grains might be finer and more uniform than expected. That's not typical for comets, whose surfaces are usually rough and chaotic. A smooth, scattering pattern suggested a surface that had been melted and then re-solidified, as if, at some point, the object had been heated past the point of sublimation and then cooled in vacuum. Could that have happened during its journey through interstellar space? Possibly, if it passed near a supernova shockwave, or through a dense molecular cloud where radiation briefly spiked. Or maybe it happened even earlier, in the fiery aftermath of its creation. Whatever the case, it carried that signature across light years, and our sun simply revealed it. To some researchers, the idea that 3I Atlas could be a relic of a violent birth fits everything we've seen. Its inconsistent outgassing, its strange surface brightness, its isotope anomalies, all could point toward an object that's been recycled by cosmic catastrophe. A fragment of a once larger world, perhaps torn from its system when two stars collided, or when a planet was shattered by tidal forces. It's hard to imagine, but not impossible. Space is full of such violence, and debris from those events would scatter endlessly, some of it eventually drifting into systems like ours. There's a quiet poetry in that idea, that as we gaze up at 3I Atlas, what we're really seeing is the residue of some ancient disaster, a world that never was, passing briefly through our sky before disappearing again into eternity. And yet in that brief encounter, it tells us something essential about ourselves, about how fragile, and yet how enduring, matter can be. Still, not everyone agrees with the exotic explanations. A few teams argue that 3I Atlas might have been an ordinary interstellar comet that simply broke apart before perihelion. The faint, steady light we saw could have been the blended signature of multiple fragments moving together, too small to resolve separately. That would explain the consistent brightness and the lack of strong jets, because what we were seeing wasn't one nucleus, but a slowly dispersing cloud. It's a practical explanation, and it fits some of the data. But others point out that even a fragmented comet should produce dust in specific patterns, and those patterns weren't clearly visible. So the mystery remains. Was it a dying ember or a solid survivor? Was the non-gravitational acceleration the last breath of sublimating ices, or a signature of something more exotic? Science doesn't rush answers to questions like these. Each hypothesis spawns a dozen more, and every observation becomes another clue in a puzzle that may take decades to piece together. What makes these interstellar visitors so fascinating is how unrepeatable they are. You can't send a probe to catch them. They move too fast. They leave too soon. By the time we spot them, they're already on their way out. Our only tools are telescopes, spectrographs, and patient curiosity, and in that way, they're like fleeting dreams, gone before we can grasp them fully. Yet, even a brief glimpse can change how we see the cosmos. When Oumuamua passed by, it forced scientists to reconsider what shapes interstellar objects could take. When 2I Borisov arrived, it confirmed that comets from other systems exist, and with 3I Atlas, we may be seeing the beginning of a pattern, a realization that interstellar space is not empty, but full of travelers, each bearing a story from another sun. Perhaps, as our detection systems grow more sensitive, we'll begin to catch them earlier, to watch them from afar as they approach, to study them before they fade. Maybe one day, we'll even send missions to intercept them. Imagine that, a probe launched from Earth, not to orbit our sun, but to chase a stranger from another star, to touch it, to read its chemistry firsthand. That's not science fiction anymore. Agencies like NASA and ESA are already developing early concepts for missions that could one day do just that. But for now, 3I, Atlas drifts farther away, its brightness diminishing with every passing week. The sun's light no longer reaches it as strongly. The instruments that once tracked it have turned to other targets. And yet, in the quiet data archives, its light curve remains, a line of numbers that, when read carefully, still hums with mystery. The story it tells is not one of immediate revelation, but of patient observation. It's a reminder that the universe rarely gives up its secrets all at once. Sometimes, understanding comes not from what we see directly, but from what refuses to make sense. In that sense, 3I Atlas is more than an object. It's a question wrapped in motion, a fragment of cosmic memory that brushed our sun, left a trace of strangeness, and then disappeared into the dark. And maybe, as you drift into sleep tonight, that's enough. To know that somewhere, beyond the edges of our reach, a piece of another star system is still moving, silent and alone, carrying within it the quiet evidence of everything that came before. When scientists talk about strangeness in space, they usually mean something that breaks the rules we thought were unbreakable. 3I, Atlas did that in small, stubborn ways. The more closely astronomers looked, the more the data began to point toward one idea that felt almost philosophical. Maybe the chemistry of other star systems isn't just a mirror of our own. Maybe the periodic table is universal, but the recipes the cosmos uses are not. When its faint light was split through a spectrograph, the ratios of isotopes, particularly the balance between carbon-12 and carbon-13, and between oxygen-16 and oxygen-18, didn't line up with the values we see in comets from our own sun's nursery. The differences were tiny but unmistakable. In the language of astrophysics, a small shift in isotopic ratio is like an accent in speech. It tells you where something grew up. 3I, Atlas spoke with an accent our solar system doesn't have. What could that mean? It might mean that the molecular cloud that formed its parent system had been enriched by a different kind of supernova, one that seeded it with slightly altered heavy elements. Or perhaps the dust that condensed there spent longer under intense cosmic radiation, nudging the isotopic balance over millions of years. The universe, after all, is not uniform. One stellar nursery might be steeped in oxygen, another might glow with excess carbon. Worlds that form in those places inherit the quirks of their birth clouds. And when a small fragment like 3I, Atlas, is hurled into space, it becomes a time capsule of that local chemistry. If we could hold a grain from it in our hands, we might see patterns in the minerals that look almost familiar. Silicates, carbonates, traces of nickel, but with ratios that whisper of a sun that shone a little hotter or lived a little shorter than ours. Even the atomic lattice could tell a story. Crystals grown in microgravity, frozen while their parent system star was still young. The idea that those atoms are now wandering through our skies feels almost intimate, like a handshake across light years. There's a quieter mystery in the way its brightness faded after perihelion. Normally, a comet brightens sharply near the sun, and then dims quickly as it retreats. 3I, Atlas dimmed more slowly, as if some internal heat continued to leak out long after sunlight should have stopped stirring it. That lingering glow may come from trapped gases slowly escaping through microfractures, or from the relaxation of stressed crystal structures within its surface. To the untrained eye, it looks like an afterthought, but to a physicist, it's evidence that matter remembers. Heat leaves traces, stress leaves echoes. Some astrophysicists modeled its motion using advanced numerical simulations, feeding in every variable they could: solar radiation pressure, rotational spin, albedo, sublimation rate, even the gravitational tides of the planets. None of the models fit perfectly. The best ones hinted that its rotation might have been tumbling chaotically, a slow, uneven spin that exposed alternating hot and cold faces to sunlight. That would explain the irregular heating pattern seen in the infrared data. It's a kind of cosmic insomnia, an object that never quite settles into a steady rhythm, forever rolling through sunlight and shadow. This erratic spin might also connect to its shape. If 3I, Atlas, was elongated, say a flattened ellipsoid rather than a sphere, then sunlight would strike it unevenly, producing torque that could gradually alter its orientation. Over time, radiation torque can make small bodies dance. On Earth we can reproduce the math easily, but out there, in the near vacuum between planets, these subtle forces become sculptors. The Yorp effect, named after the scientists Yarkovsky, O'Keefe, Radzievsky, and Padak, describes how light can spin an asteroid faster or slower. For something as lightweight as 3I, Atlas seems to be, the Yorp effect could be dramatic. It may have turned slowly for eons, then accelerated, cracking under its own rotation like a piece of brittle glass. That possibility leads to another question. If it fractured long before entering our solar system, could its current shape be only one shard of a much larger body? Somewhere out there, perhaps hundreds of trillions of kilometers away, other fragments could be drifting on parallel paths, each with its own faint trail of dust. We'll likely never find them, but the thought is strangely comforting. The idea that 3I, Atlas, might not be alone. Even interstellar wanderers may travel in families. On the quantum scale, the same physics that drives its motion also reveals the nature of light itself. Every reflection from its surface was a conversation between photons and electrons, a microscopic dance governed by quantum mechanics. When those photons bounced back toward Earth and were captured by our detectors, they carried the imprint of that dance. The absorption lines, the scattering angles, the polarization states. Each of those details encodes the probabilities of quantum transitions happening trillions of times per second on grains of alien dust. We don't often think of it this way, but observing an interstellar object is a direct experiment in quantum electrodynamics conducted across billions of kilometers. If we push that thought further, we arrive at something deeper, the realization that the universe isn't a vast emptiness filled with occasional solid things. It's an unbroken web of interactions, from the quantum jitter of electrons to the gravitational ballet of galaxies. 3. Atlas happens to sit at the intersection of those scales. It's large enough to follow classical physics, yet small enough that quantum processes, radiation pressure, tunneling of volatile molecules, photon recoil, still shape its fate. The boundaries between classical and quantum blur there, the way dawn blurs the line between night and day. That blending fascinates scientists who study the physics of small bodies. They see in 3I, Atlas, an opportunity to refine models of non-gravitational dynamics, a field that lives at the edge of chaos theory. In their equations, every photon counts, every collision with a dust grain matters. By comparing its motion to simulations, they can test how well our understanding of momentum exchange at the quantum level scales up to macroscopic bodies. In other words, an icy rock from another star becomes a laboratory for universal physics. Some researchers propose that 3I, Atlas, might have accumulated a thin layer of organic compounds, complex hydrocarbons formed by ultraviolet radiation, acting on simple ices over millions of years. Such a coating, called tholin, is known to exist on outer solar system objects like Titan and Pluto. Tholins darken a surface but can also seal it, trapping gases underneath. If 3I, Atlas, carried a similar crust, it could explain the muted outgassing and the delayed brightness changes. The heat from perihelion might have seeped through slowly, releasing material in a controlled exhale rather than an explosion. The result would be exactly what we saw, a comet that seemed too calm, too measured. In the lab, when scientists simulate tholin formation, they create rich, tar-like residues, complex, carbon-based molecules that absorb light across the visible spectrum. Some of those molecules are precursors to amino acids. So in a quiet, roundabout way, 3i, Atlas reminds us that the chemistry of life isn't confined to Earth or even to our sun's domain. The building blocks are scattered everywhere, drifting between stars, attaching themselves to any rock that happens to pass by. It's entirely possible that objects like this have been delivering organic compounds to countless worlds for billions of years, seeding them with potential. That idea has a name, panspermia, the hypothesis that life, or at least the chemistry that leads to it, spreads naturally through space on the backs of comets and asteroids. 3i. Atlas isn't proof of panspermia, but it's a beautiful reminder of why the concept persists. Every interstellar object is a courier. Every perihelion is a handoff between systems. The dust it sheds might someday fall onto another world, carrying with it the traces of its alien birthplace. In that sense, the cosmos is constantly exchanging letters written in carbon and hydrogen. As telescopes continue to scan the sky, new programs are being designed to catch the next interstellar messenger. When that happens, scientists will know what to look for. The subtle shifts in light, the spectral lines that tell of different isotopic stories, the whisper-thin push of radiation pressure. And each new discovery will add a line to the ongoing dialogue between stars. For now, though, our understanding comes from inference and imagination. 3i. Atlas has faded beyond reach, its signals swallowed by distance and solar glare. But the models continue to evolve. Every data point we recorded, every photon captured by a CCD sensor, is still being reanalyzed with new algorithms, new ways of teasing meaning from noise. Somewhere in that digital noise, hidden beneath the uncertainty, may lie the explanation for why it behaved so strangely near the sun. Maybe it's all chemistry, maybe it's the subtle geometry of a fractured shell, or maybe it's a phenomenon we haven't named yet, waiting for us to notice it again when the next traveler arrives. Until then, the mystery remains open, suspended between hypothesis and wonder, and that, perhaps, is the best place for it to live. Because science grows not from certainty, but from curiosity, the quiet kind that keeps you awake a little longer, staring into the dark, thinking about an object that came from another star and left us with questions that sound almost like lullabies. When we look out at the night sky, it's easy to think of the solar system as a neat, well-defined family of planets circling the sun, each on its orderly path. But in truth, the edges of that family are soft and uncertain. The gravitational pull of the sun fades slowly, like the dying echo of a bell. Somewhere out there, at the farthest reach of its influence, lies the Oort cloud, a vast invisible sphere of icy fragments, millions of times farther away than Earth. Beyond it begins the domain of other stars. 3i. Atlas crossed that boundary, entering our neighborhood from the great in-between, the region we call interstellar space. The Oort cloud itself is more a concept than a confirmed structure. We infer its presence from the comets that occasionally fall inward, as if drawn by some unseen tide. Every time one appears, it carries hints of that remote reservoir, its composition, its orbit, its age. Yet, until interstellar visitors like 3i Atlas arrived, we could only guess whether our cloud was typical. Was every star surrounded by such frozen halos, or was ours an exception? Each new interstellar object helps answer that question. By tracing their paths backward, scientists begin to map a faint web connecting stellar systems. A web of debris, each thread a potential traveler. It turns out that the space between stars isn't empty at all. It's filled with wanderers, grains, shards, comets, orphaned moons. Some drift for billions of years before colliding with another star's domain. 3 Atlas is one of those drifters, an ambassador from the space beyond the sun's light. When its trajectory was calculated, astronomers noticed how effortlessly it sliced through the sun's gravitational field. Its velocity, about 26 kilometers per second relative to the sun, was too high to have been captured. It came in, curved gently, and left again, a single graceful arc. That simplicity makes it a perfect tracer of the invisible boundary we call the heliopause, where the solar wind gives way to the interstellar medium. Beyond that invisible frontier, Particles no longer feel the sun's breath, they move to the rhythm of the galaxy itself. For a brief time, 3I, Atlas became a messenger from that outer realm, carrying data about conditions we can't reach directly. Scientists studying the heliosphere compare it to the wake of a ship moving through cosmic water. The sun's magnetic field and solar wind carve out a bubble in the galaxy's gas and dust. Every so often, something from outside passes through the boundary, giving us a chance to measure how thick or porous that border is. The way 3I, Atlas responded to solar radiation, the way its coma formed, the way it reflected light, hints at the density and composition of the interstellar dust it had traveled through. By reading those clues, researchers can refine their models of the local galactic environment, the space between stars. It's humbling to realize that a single rock, barely large enough to fill a small valley, can teach us about phenomena stretching across light years. Its journey sketches a connection between two suns, maybe more, from the cloud that birthed it to our own star, and then back out again into the dark. The boundaries of our solar system become less like walls and more like the surface of a pond disturbed by ripples from many directions. The encounter also reshapes how we think about planetary origins. For decades, astronomers assumed that planet formation was mostly a closed process. Dust collects around a single star, clumps into planets, and the leftovers remain nearby. But interstellar objects suggest a more open exchange. Systems share material. The galaxy itself behaves like an ecosystem, where fragments migrate from one nursery to another. Some of the atoms that make up Earth could once have belonged to another star. In that sense, every world is an adopted child of the cosmos. 3I, Atlas gave us a small but precious dataset to test that idea. The way its light scattered in the infrared implied that its dust grains were unusually fine, smaller than a micrometer across, and possibly coated in carbon compounds that absorb heat efficiently. Those properties match the outer layers of protoplanetary disks seen around young stars. It's as if the object had been frozen mid-formation and then expelled before its world was complete. That tells us that planet building is messy. Systems throw material away as often as they gather it, and some of that debris eventually finds its way here. In that context, our solar system is not isolated, but porous. Every so often, matter from beyond slips in, and some of ours slips out. Jupiter's gravity, powerful and far-reaching, can fling comets outward fast enough to escape forever. Those exiled fragments become interstellar travelers themselves, carrying traces of our own sun into the galaxy. Perhaps somewhere, another civilization is watching one now, wondering where it came from, building stories about the star that birthed it, just as we're doing tonight. When astronomers model the population of such travelers, they find that space could be teeming with them, millions of objects drifting silently between stars at any given time. Most are too small or too dark for us to see. But statistically, Earth's orbit should cross paths with one every few years. That means 3I, Atlas, wasn't a once-in-a-lifetime visitor. It was the first of many we'll detect as our technology improves. Each new detection will refine our sense of how material circulates through the Milky Way, turning the galaxy from a static backdrop into a living, breathing system of exchange. To think of the galaxy this way, as a connected whole, changes our sense of home. The solar system stops being a lonely island and becomes one node in a vast archipelago. The Oort cloud marks not an edge but a shoreline, where the tides of the galaxy lap against the gravity of the sun. 3I, Atlas was a wave that crossed that shore, reminding us that boundaries are illusions of distance and scale. Even the way light from distant stars interacts with these wandering objects tells us something about the architecture of our surroundings. When starlight passes through the coma of an interstellar body, it's filtered, its spectrum shifted by the dust's properties. Comparing those subtle shifts with background stars allows scientists to map how interstellar dust changes from place to place. In essence, every traveler becomes a sampling probe, carrying with it the signature of the medium it moved through. As you picture 3I, Atlas sailing away from the sun, imagine the environment it's re-entering, a region filled with charged particles from ancient supernovae, threads of magnetic field lines stretching for light years, pockets of cold hydrogen gas. Out there, cosmic rays streak endlessly, colliding with stray atoms, forging new isotopes. The object will continue to weather those impacts, slowly altering its surface once more. Over millions of years, its features will erode, its chemistry will evolve, until one day it may drift close to another star and begin the story again. From that perspective, interstellar space isn't a void, but a long-distance conversation among suns. Every object that crosses from one system to another carries messages in the form of elements and minerals. The Milky Way is exchanging matter constantly, like a heartbeat pumping stardust through its veins. 3I. Atlas just happened to brush against us on one beat of that rhythm. For astronomers, this realization brings a new kind of humility. The solar system is not the center of anything, it's a transient pattern in a much larger flow. Yet it's within that pattern that life arose, looked up, and began to ask questions. When we study 3I, Atlas, we're really studying ourselves. The ingredients that built our world, the physics that sustain it, the cosmic currents that might one day carry fragments of Earth outward to someone else's sky. So as you listen, maybe with your eyes half closed, imagine the boundaries of our home dissolving. Picture the sun not as a solitary beacon, but as one light among billions, its warmth extending just far enough to greet an occasional traveler, somewhere beyond Neptune, beyond the last whisper of solar wind. 3I. Atlas is already a faint spark against the stars, its orbit bending away, carrying the story of its brief encounter. In that fading spark lies a reminder: our solar system is not a cage but a crossroads. Every encounter, every anomaly, is a sign that the universe is alive with movement and exchange. When scientists trace the trajectories of objects like 3I, Atlas, they're not just mapping motion. They're looking for clues about time, how the universe built its structures, and how long those structures have been trading material. The atoms that make up your body, carbon, oxygen, nitrogen, iron, were forged in the hearts of stars that lived and died long before the sun existed. But the way those atoms came together, the particular mix that makes Earth what it is, depends on the flow of debris through the galaxy. Every comet, every interstellar rock is a record of that flow. When 3I, Atlas passed through, it carried a signature from a different neighborhood of the Milky Way, a snapshot of conditions under another star, frozen billions of years ago. To study that material, even indirectly, is to reach across time and distance. The ratios of isotopes in water ice, the presence of certain organic compounds, the reflectivity of the dust, all of it becomes a kind of cosmic fingerprint. When astronomers compared the light spectrum of 3I, Atlas, to those of known comets, they noticed subtle mismatches. Certain infrared absorption lines didn't fit our models of solar system ices. That meant its chemistry had evolved in an environment with slightly different radiation, perhaps under a cooler or older star. In that way, 3I, Atlas became a time capsule from a place we'll never visit. The implications stretch beyond curiosity. If organic molecules, the raw ingredients of life, can survive ejection from one system and travel through interstellar space for millions of years, then life's building blocks could be widespread. The concept is called panspermia, the idea that the seeds of biology are scattered through space, riding on comets and dust. 3I. Atlas didn't carry life, at least not as far as we can tell, but it carried the chemistry that makes life possible. Each such traveler expands the probability that somewhere else, under another star, similar reactions took place. When we look at it that way, the discovery of interstellar objects is less about mechanics and more about connection. Every one of them is evidence that no world forms alone. Even the smallest particle is part of a galactic economy, atoms exchanged, rearranged, reborn. You could say that 3I, Atlas, is a wandering page in the story of life's origins, written in frozen carbon and dust. Its perihelion, its moment near the sun, gave us a glimpse of the script before it drifted away again. As the object approached the sun, solar radiation began to heat its surface, releasing gases and dust into a faint coma. Instruments tuned to ultraviolet wavelengths detected signatures of cyanide, water, and carbon monoxide. These aren't unusual for comets, but the ratios were peculiar: too much cyanide compared to water vapor, and almost no methanol. On Earth, such compounds are part of prebiotic chemistry, the chain of reactions that could lead from simple molecules to amino acids. Their imbalance in 3I. Atlas hinted that its parent system had different conditions for chemical evolution. That alone is an extraordinary discovery. It means that organic synthesis can follow multiple paths. The universe is versatile in the recipes it uses to build life's ingredients. Astronomers like to think of each interstellar comet as a laboratory. It's a way to study environments we can't otherwise reach. 3I. Atlas told us that not every system enriches its outer regions with the same compounds we have. Maybe in some systems, icy bodies carry more carbon chains. In others, more ammonia or sulfur compounds. That diversity hints that if life emerges elsewhere, it could be chemically distinct, based on the same universal physics but different starting ingredients. The Perihelion, that closest approach, was a gift to spectroscopy. As the sun's heat peaked, layers of the comet's crust peeled away, exposing material that had never been touched by radiation before. Telescopes captured those fleeting hours of outgassing, analyzing the released particles. What they found surprised even seasoned researchers: traces of isotopic oxygen ratios inconsistent with the solar system norm. This was proof, carved into the spectrum itself, that 3I, Atlas had not formed here. It was born under another sun, a different nursery altogether. Think about what that means. For the first time in human history, we're not just studying our own cosmic backyard. We're analyzing samples from another planetary system. No spacecraft required, no interstellar mission needed. The travelers come to us, carrying fragments of their home worlds. And they do it silently, unannounced, until one day our telescopes notice a faint point of light moving too fast, at an angle that doesn't fit. That realization shifts the scale of exploration. Space isn't a distant frontier we're reaching toward. It's a network we're already connected to. The solar wind, cosmic rays, drifting comets, they're all part of an ongoing exchange. 3I, Atlas made that visible. Its strange perihelion behavior wasn't just a curiosity. It was a message about how dynamic, how alive the galaxy really is. There's also something beautifully paradoxical about the way we study such objects. They move fast, too fast to intercept, and they're gone before we can prepare missions. Yet in that fleeting passage, they offer a kind of intimacy. For a few months, all of humanity's eyes are turned toward a single moving dot, tracking its every shimmer. In that shared focus, borders disappear. We become, for a moment, a species united by wonder. If you close your eyes and imagine it, a glowing arc sweeping across the black, sunlight glinting off a surface older than Earth itself, you can feel the strangeness of it. A traveler from another star, passing so close we can touch its light. Its chemistry whispers of alien worlds. Its orbit curves through the sun's gravity well, like a visitor pausing to greet us before returning to the void. It asks nothing of us, leaves nothing behind except data and awe. And yet, in that awe, something awakens. Each discovery like this sparks new missions, new technologies, new dreams. The next time an interstellar object is spotted, we'll be ready, with faster probes, better telescopes, more sensitive instruments. We'll send missions to chase them, to sample them, to touch the material that once orbited another sun. When that day comes, it will feel like shaking hands with another world. In a way, 3I, Atlas's strange behavior, the uneven brightness, the inconsistent gas emission, was a challenge. It reminded us that the universe doesn't always fit our neat categories. It breaks the patterns we expect, forcing us to rethink what we know about comets, stars, and the boundaries between systems. And that's the heart of science, not the answers we already have, but the questions that refuse to be quiet. So when the data streams faded, when the object receded beyond our telescopes, astronomers didn't feel loss, they felt invitation. An open question left drifting among the stars, waiting for the next traveler to pass by. When 3I, Atlas, slipped through the inner solar system, something in its motion quietly disobeyed our expectations. Its acceleration curve, measured across multiple observatories, showed a subtle but persistent deviation, not large enough to rewrite physics, but enough to make scientists pause. The pattern echoed the anomalies once seen with Oumuamua, the first interstellar visitor we ever detected. Like its predecessor, 3I, Atlas seemed to move as though nudged by a force too gentle to name. At first, the simplest explanation was outgassing, jets of vapor escaping from beneath its crust, pushing it slightly off course. It's a familiar phenomenon among comets. But the numbers didn't fit neatly. The amount of gas required to produce that acceleration should have brightened the object's coma far more than we observed. It was as if something invisible was guiding its path. Not enough to be mystical, just enough to remind us that the universe still hides subtleties in its physics. This led to a wave of hypotheses, some elegant, some bold. Could the dust structure on its surface be reflecting solar radiation unevenly, producing a tiny but measurable push? Could it be a fragment so porous that sunlight itself passed through and around it in unpredictable ways? Or, and this was the daring thought, could we be witnessing the first evidence of matter interacting differently with the faint presence of dark matter in our local region? Dark matter is one of the universe's most profound mysteries. It neither emits nor absorbs light, yet its gravitational influence shapes galaxies, bends starlight, and anchors cosmic structures. The Milky Way swims in a vast halo of it, an invisible ocean through which the solar system drifts. Objects passing through this medium might feel minuscule, localized variations in gravitational density. If 3I, Atlas's motion responded to that, if its trajectory subtly traced the gradient of the unseen, it would be the first natural probe of dark matter at the scale of an interstellar rock. Of course, that's speculation, and scientists are careful with speculation, but the beauty of discovery lies in these questions. Every unexpected measurement is a keyhole into something deeper. Atlas wasn't a laboratory in the traditional sense, but it was an experiment set in motion by the cosmos itself. The sun, the object, the dust, the light, all combined to produce data we could only interpret by expanding our imagination. What makes the dark matter theory compelling isn't the anomaly itself, but its timing. Around the same years that 3I, Atlas was observed, astrophysical surveys detected slight irregularities in the distribution of local dark matter density near the solar neighborhood, fluctuations that could, in theory, exert non-uniform gravitational tugs on objects traveling at interstellar speeds. Most celestial bodies in stable orbits wouldn't reveal such subtleties, but something on a one-time flyby might. Something like 3I, Atlas. Even if dark matter wasn't directly responsible, the question sharpened our tools. Astronomers refined models of solar radiation pressure, material porosity, and outgassing dynamics. The result was a clearer understanding of how sunlight, gas, and dust interact across vast distances, knowledge that now informs spacecraft design, asteroid tracking, and even the planning of missions beyond the heliosphere. The strangeness of 3I, Atlas also reignited interest in how interstellar space itself behaves. We often picture the void between stars as calm and empty, but it's threaded with magnetic fields, currents of charged particles, and turbulence at scales that span light years. When a small body moves through that medium, it experiences drag and pressure, not unlike a ship sailing through a gentle current. Perhaps 3I, Atlas's anomalies weren't caused by something exotic at all, but by the subtle push and pull of the interstellar plasma, invisible yet omnipresent. Still, the numbers left a trace of mystery, not large enough to call it a discovery, but enough to whisper that we might be missing something. And that whisper is what keeps science alive. Every era of discovery begins with such whispers. When Uranus's orbit didn't fit Newton's predictions, astronomers searched for another planet and found Neptune. When Mercury's orbit deviated slightly from expectations, Einstein's relativity emerged to explain it. Maybe 3I, Atlas is another such messenger, a subtle nudge toward a deeper framework, one that unites gravity, light, and the unseen. Beyond the technical debates, there's a more philosophical layer to its mystery. The way 3I, Atlas moved, calm, deliberate, unhurried, felt almost like a metaphor for knowledge itself. It entered our awareness quietly, stayed just long enough to provoke new thinking, and then faded back into the dark, leaving us changed but uncertain. Science, too, moves that way, not in leaps, but in gentle, continuous corrections of understanding. As its brightness dimmed and it drifted beyond the reach of our telescopes, astronomers continued to model its path mathematically, extending its orbit years, even centuries into the future. They traced it beyond the outer planets, through the Kuiper Belt, past the heliopause, and out again into the galactic sea. In simulations, its trajectory curved through the local stellar neighborhood, eventually crossing regions of space where no human probe will ever go. Perhaps millions of years from now, another civilization will detect it, a faint moving dot from another sun, carrying traces of our light on its surface. They might notice the same odd acceleration, the same strange chemistry, and wonder what secrets it hides. In that sense, 3i, Atlas is more than an object. It's a bridge across epochs of curiosity. It connects observers who will never meet, separated by time but united by wonder. The something strange it exposed at Perihelion wasn't a single anomaly or discovery. It was the realization that even in an age of data and precision, the universe still resists full explanation, and that resistance is a kind of beauty. It's what keeps us watching the skies, building better telescopes, asking deeper questions. As night falls and you listen, picture that silent traveler far beyond the sun now, its faint surface glimmering with a memory of our warmth. Whatever strange forces guided its path, sunlight, dark matter, magnetic tides, or something we haven't yet named, they're part of the same cosmic rhythm that moves galaxies and atoms alike. And somewhere in that rhythm, we find ourselves asking what it means to be aware in a universe that still surprises us. Because maybe that's the real message. 3i, Atlas carried, not proof of dark matter, not just data, but a reminder that wonder is the first step of understanding. That curiosity, quiet, patient, endless, is how the universe comes to know itself. As the years pass and 3i, Atlas fades from our telescopes, it becomes something quieter, a memory wrapped in mathematics, a faint trace in the archives of observation. The numbers remain, its speed, its orbit, its curious drift at perihelion, but beyond the data lies a story, one that science records and imagination completes. Somewhere in the cold beyond Neptune, where sunlight weakens into starlight and then into darkness, that traveler is still moving. It carries with it the dust of its home system and, now, the soft echo of ours. There's something profoundly humbling about that image, a small fragment of another world passing through the light of our sun, tracing a perfect curve through space and continuing on, untouched and unchanged. In that moment, for all our technology and knowledge, we were simply witnesses. The universe opened a small window, just long enough for us to look through, and then closed it again. Maybe that's how it has always been. The cosmos offers glimpses, never the whole picture. We catch the light, decode the signals, build stories from silence. And every time we think we're close to understanding, another visitor, another anomaly, reminds us how vast the unknown still is. Atlas's strange behavior at perihelion wasn't a flaw in the equations, it was an invitation, a reminder that reality is richer than our models. Even now, scientists revisit the data, refining the simulations, testing new theories. Some see in it a lesson about how interstellar dust interacts with radiation. Others, a potential insight into unseen physics. But beneath those layers of analysis lies something deeper, the quiet acknowledgement that we are part of the same cosmic story. The same forces that guided that object through the stars shape us too. The same gravity, the same photons, the same atomic laws that govern its orbit run through every cell of our bodies. It's strange to think about. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were born from stars long dead, scattered by explosions across the galaxy, gathered again in the cloud that became our sun. We are, in the most literal sense, made of stardust. When we study 3i, Atlas, we are studying our own origins, the materials and processes that made consciousness possible, and maybe that's why stories like this matter. Not just because they expand our scientific boundaries, but because they reconnect us with wonder. For a species that has walked on the moon and peered into black holes, wonder might seem unnecessary, but it's not. Wonder is how knowledge begins. It's what keeps us looking up when the night feels endless. So as you lie there listening, imagine yourself floating in that interstellar dark. The sun has become a tiny spark behind you, around you silence, not empty but full of invisible currents and ancient light. Ahead, a single faint glow, 3i, Atlas, gliding onward, its surface reflecting the last shimmer of our star. You are drifting with it now, side by side, carried by momentum through a galaxy alive with motion. Out here, there is no up or down, no before or after, just motion and memory. You can almost hear the rhythm of cosmic time, the pulse of stars being born and dying. The endless conversation of light and gravity. The same rhythm moves through your heartbeat. The same energy that turns galaxies also fires the neurons behind your eyes. You are not separate from the universe. You are one of its ways of knowing itself. And as that realization settles in, you can let go of the noise, of the smallness, of the constant need to understand. You can rest in the fact that mystery is not an absence of knowledge, but a presence, a space for awe, for humility, for sleep. Somewhere, 3i, Atlas continues on, untouched, unhurried. It doesn't need to know where it's going. It just follows the quiet instructions written into the laws of physics, the same ones written into you. Every rotation, every reflection of sunlight, is part of a pattern too vast to see all at once. And tonight, you are part of that pattern too. The same gravity that pulled that object toward our sun pulls you gently toward rest. The same universe that sent it through our skies surrounds you now, silent and infinite. You don't need to chase it. You don't need to solve it. Just listen to it. The slow drift of stars, the patient heartbeat of time. Because in the end, that's what 3i, Atlas, taught us. That the universe is not cold or distant. It's alive with motion, filled with travelers, and whispering to anyone who stops long enough to listen. It doesn't shout its secrets. It hums them softly, through comets, through light, through the long, graceful curve of an orbit. And maybe that's enough. So close your eyes now. The sun fades to a faint warmth in your memory. The stars unfold around you. Somewhere far ahead, a small light keeps moving, quiet, steady, eternal. That is 3i, Atlas, carrying the story of our encounter into the dark. And as it goes, so do we, drifting, dreaming, wondering. Good night, traveler. Good night, universe.